Since we saw or we have understood about what big O is, the next important notation is called it as the big theta. So it is written as theta of something, right? So again, the definition is going to be very similar. If you understand the big O notation, then big theta should be a very straightforward one, right? So same like how I have shown the graph for big O, let me show you a graph for big theta as well. Then we'll understand the mathematical explanation from this graph. So same like how we have learned for big O notation. So imagine I have a graph, and the x-axis represent the value of n here, and the y-axis for time or the space. So y-axis represent the time or space. Suppose I have a curve, so this green color curve, which represent f of n. Now comes the interesting part here. So assume that we have the two more functions, one which is c1 into g of n and another one which is c2 into g of n. So this is my n0, so n naught. So unlike the big O case, right? So if you look at the big O notation, big O graph, here we had only one bounding curve above the f of n. So in case of theta, we have the two curves, right? So one above f of n and another one is below the f of n. Now let me state the formal definition and then we will connect it to the graph. So we say that f of n is equal to theta of g of n if and only if, so I'm often represented it as if and only if, IFF, which represent if and only if there exist three constants, right? So in this case, here we have the three constants. What are those three constants? N0, C1 and C2 such that my C1 into G of n is greater than or equal to 0. That means 0 is less than or equal to C1 into G of n, which is also less than or equal to f of n, and f of n is less than or equal to C2 into G of n for all values of n is greater than or equal to n0. So this is the mathematical definition of a big theta. Now let us understand what this means. So if you look at this definition, here I have the three constants n0, c1 and c2, right? Such that for all values of n is greater than or equal to n0, my f of n is lower than c2 into g of n. So if you take any value of n, right, my f of n is always lower than g of n here, and your f of n is always greater than c1 into g of n, right? That means and also c1 into g of n is always greater than or equal to 0, right? So this is my 0, and this function for any value of n is greater than or equal to n0. So this function is always greater than or equal to 0 here. So what is saying here is just by changing the constants slightly, right? So by changing the value of constant like c1 or c2, right, my f of n is greater than or equal to c1 into g of n for one constant, and f of n is less than or equal to c2 into g of n for another constant. So if this so, then we can say that my f of n is equal to theta of g of n. For all values of n is greater than or equal to n0, the function f1 lies between c1 into g of n and c2 into g of n. So if you think about the intuitively, what this is saying in case of big O, so if you look at the big O case, my f of n can't be greater than c into g of n. So I would say that my f of n is upper bounded by g of n here, right? So my f of n is upper bounded by g of n. So in case of theta of n, it is saying that f of n is for different constants, so c1 and c2 is tightly bounded. So I would say that it's a tightly bounded on both sides by g of n by just changing the constant slightly, right? I hope you understand the definition of a big theta. Now let us move to the third notation, which is a big omega, right? So big omega is defined similar to what we have learned for big O and big theta. Again, I'm just giving the diagram here so that we can easily understand the definition of big omega. And big omega is often referred as this. This is the Greek symbol, right? Now suppose we have f of n, right? So again we have on x-axis represent the value of n and the y-axis represent the time or the space here, right? Now suppose I have a function f of n. So the green color curve represent the f of n here. Now assume there exists a constant c such that c into g of n is always below the f of n for all value of n is greater than or equal to n0. So this is my n0. For all values of n is greater than or equal to n0, c into g of n is always less than or equal to f of n. So formally we can say, as per the definition of big omega, I can write it down as f of n is equal to big omega of g of n if and only if, I'm just writing down as IFF, it represent if and only if there exist a constants c and n0 such that and my c into g of n is greater than or equal to 0. That means 0 is less than or equal to c into g of n, and c into g of n is less than or equal to f of n. My f of n is always greater than g of n for all values of n is greater than or equal to n0. So this means my f of n is always a constant multiple of g of n for sufficiently large n, right? So here you can say that f of n is always going to be a greater than c into g of n, or I would say f of n is always going to be a lower bound, right? So this is the lower bound by g of n with some constant c. So in case of big O, we have the upper bound, right? So big O is the upper bound. Let me write it down here. Upper bound. And what about a big theta? Big theta is the tightly bound. Tightly bound. And what about omega? Omega is lower bound. Lower bound. So tightly bound means it has both upper and the lower. It has both upper and lower. So in simple terms, I would say big O says that my f of n does not grow faster than g of n, right? So c into g of n is always greater than or equal to f of n in case of big O. So in case of big omega, c into g of n is always less than or equal to f of n. So f of n doesn't grow slower than g of n. And big theta says that, this is for big omega. And big theta says that f of n grows at the same rate as f of n, g of n, right? So that's why it is called it as the tightly bound. So whenever you think about the big O or big theta or big omega, it is very helpful to visualize the graphs. So just need to visualize the graph. You don't need to memorize the formal definition of each and everything word by word. If you remember the idea of upper bound, lower bound and the tight bound through this simple diagram, you will understand and recall these concepts much more easily. So that is the simplest way to remember all of these notations, right? And by the way, these graphs I took it from the CLRS book. This is one of the best book where you can find the best visualization of these